Okay, so the topic I'm going to talk about is not molecular, is not electronic, is not structural. Okay, it's a completely different topic, which I hope some people can actually connect with and use in the future. So anyway, the topic is vector extrapolation methods or convergence acceleration methods for the solution of large systems of equations, linear or nonlinear, especially nonlinear. Okay, so here we are. This is a topic that I have been working on for the last 40 years on and off. And I published quite a few papers on different aspects of the topic, including development of methods, numerically stable and economical algorithms for their implementations, their convergence and stability analyses, and some applications also. Anyway, so here, the problem is as follows. I mean, the problem that will be interesting to you is as follows. We have a system of linear or nonlinear algebraic equations, okay? The dimension of the space we're working in is capital N, and capital N for these applications is a very large number. When I say large, I mean it can go up to millions, tens of millions, even to billions, for example, as in the case of the PageRank of the Google Web Matrix. Okay, so normally what you would do is you would rewrite this equation system in the form x equals f of x, which makes it very convenient for applying fixed point iterations. So you choose a nice function f out of these equations, and you start with a initial vector x0, which you choose, okay, and then you iterate like this, hoping that the vectors are approaching actually the solution of the system, which is S. Now, in case of convergence, of course, the limit of the sequence will be equal to S. It has no other choice if F is a continuous vector value function. Okay, and this will happen only when the Jacobian matrix of the equations f of x of the functions f of x at the solution has a spectral radius which is less than 1. Okay, in case of divergence, which can also take place, then we call S the anti-limit because the vectors of iteration are actually getting far away from S. Okay, they're starting with S, for example. You can imagine that way, and then they're going to the two other places.
Please explain what you mean by rho.
Sorry?
Please explain what you mean by rho.
By rho? Rho is, okay, this is a notation of linear algebra. Rho of a matrix, or a square matrix, means the modulus of the largest eigenvalue of the matrix, which is called spectral radius of the matrix.
Thank you.
Okay, yeah. So normally, in most problems of interest, the convergence of the sequences are very slow, sometimes extremely slow. You may have to perform many iterations to get to maybe a few digits of the correct digits of the solution itself. So what you want to do is you want to accelerate the convergence of the sequence that you obtain. You don't want to do anything to the sequence. You just want to take some elements of the sequence and process them in a way that will give you a much better approximation to the solution, or to the limit rather here, instead of each one of the vectors that you're using to obtain that. Okay, so we can accelerate the convergence of the sequence by using what we call vector extrapolation methods. So there are two types of vector extrapolation methods, polynomial ones and epsilon ones. The epsilon ones were the very first ones, actually. You can see these are from about 70 years ago, something like that. Okay, 60, 70 years ago. And the other ones are they came into existence later. And the last one is the one that I developed, which I call the SVD MPE. Basically means singular value decomposition based MPE. Now, MPE is the minimal polynomial extrapolation. RRE is the reduced rank extrapolation. There's also MMP, modified, etc. So I'm not going to talk about too much on this. What I want to say is that why do I state about polynomial and epsilon algorithms? I just want to make the statement that polynomial methods are preferable for systems of equations. They're much more economical than epsilon algorithms as far as computation and also storage, computer storage is concerned. Okay, and what I want to talk about is MPE, RRE, and SVD-MP because these three methods, they all rely on some solution of least squares problems. And their algorithms can be unified in a certain sense, as I will show you later. Okay, anyway, there are many areas of application of these methods. Here's a short list. There are more, but I think this will be enough to actually drive the point that that these are really very useful methods and they're being used in many, many different computations. Okay, this is the book that I published 3 years ago. It contains all the material that I knew about in up to 2018. Okay, and it's a SCIEM publication. Okay, this is the computational science and engineering series of SCIEM. Anyway, so for all polynomial methods, what is generally common to them is that you take the vectors x0, x1, x2, etc. Okay, and then you make a linear combination of those like this. The sum of the gammas is equal to 1. Okay, and this vector is the one that you're interested in. This is the thing that is approximating your solution S, if you will. Okay, now of course the gammas are nonlinear in the extravents. They're highly nonlinear actually. And each method has its own way of developing the gammas. Okay, and to determine this vector, all you need is k-square vector operations, meaning k-square vector additions, scalar vector multiplications, or Saxby operations, and the dot product. Okay, and the input is these vectors x0, x1, or xk plus 1. So you need one more vector actually. So k plus 2 vectors, this is all you need to obtain this thing here. And the epsilon algorithms, you see, they're 6 times more expensive computationally, and the storage-wise, they're twice as expensive as the polynomial methods. Okay, so the general description of the methods runs as follows. You take the vectors x0, x1, etc. You form the forward differences. Then you form this matrix here, which is a triangle, sorry, a rectangular matrix. Has n rows and k plus 1 vectors. K is a very small number. Now, n may be in the thousands, 10,000, 100,000, etc. Okay, and even more than that. K is a number like 10, 20, 30, 40, something like that. Okay, it never goes up to 100 even in all applications that I'm aware of. So this matrix has k plus 1 vectors, columns, and the rank is k plus 1. This is what we're assuming, because at some point it becomes rank deficient, okay, and we're not going to end up at that point with the values of k that we have. So Sk is this combination here, and then we also have the combination of the u's, which I write in terms of matrices, uk times gamma. Gamma is this k plus 1 dimensional small vector. Okay, you can also express the matrix, the vector Sk in this form, which is very convenient computationally. In the algorithms, in all the algorithms, I use this thing here that turned out to be extremely useful to save storage, computer storage. Yeah. Sorry, somebody was at the door. Okay, so once you have the gammas, you can compute the size by using these expressions here, and then you can form your S sub k. So the residual vector is f minus x. F of x minus x is the residual vector because at x equals s is 0. If x is slightly different than s, then it's going to be a small vector. Now, it turns out that this vector here, u sub k times gamma, where are we? Here. Okay, this vector here is actually the residual vector for a linear system. And it's an approximation, a true first order approximation to the residual vector of if f is nonlinear. So we'll be using here the norm, okay, induced by the L2 inner product. So MPE is defined as follows. We have this matrix UK that you've seen before, we define a vector C, okay, a k plus 1 dimensional vector. The first k minus 1 components I call C prime. Now I solve this linear least squares problem here, okay? Which I express also in terms of matrices like this. I said C sub k is equal to 1 because C sub k is actually the coefficient of U sub k in this expression. And then I compute the gammas as follows. This way, the sum of the gammas is equal to 1, of course. And then this is the approximation for MPE. Of course, this exists provided the denominator here is non-zero. Otherwise, it does not exist. That's possibility. Okay, the RRE is defined in a slightly different form. Again, you start with the matrix U sub k. This is the gamma, the vector of the gammas. So you minimize this subject to a linear constraint now. The previous one didn't have any constraint. So this is your linear constraint, okay? You solve for the gammas, and then you form this thing here. So it always exists, because this problem here always has a solution which is unique. Okay, and then SVD MPE, as before, we have a vector C, k plus 1 dimensional vector. We solve this minimization problem here with this constraint. Okay, in matrix form, this is the one. Okay, and then once you get your C, you compute the gamma i's like this, and then you form your approximation. Now, what is the C? What is the solution here, C? So you take your matrix U sub k here, you take a singular value decomposition. The smallest singular value, okay, has corresponding right singular vector and left singular vector, okay? So the right singular vector corresponding to sigma k, which is 8 sub k, that is your C. Okay, this is the C, and then you form with the C, you form the gammas. So anyway, now I'm going to skip this one here. How much time do I have, please? How much time do I have?
You have 12 minutes.
Okay, so I think I'll just mention how do we do the algorithms for these. So to do the algorithms, I form the QR factorization of the matrix U sub k. Okay, this is the unitary matrix, a rectangular unitary matrix. This is the square matrix R sub k. So this is a very small matrix, k plus 1 by k plus 1. This is n by k plus 1. Okay, so each time I add a vector, I add a column to the q's, to the q sub k, and I add a row and a column to R sub k. So this is, the updating is very, very, very easy. So you can actually choose the k after you've done this. And for MPE, you solve, see the steps 0, 1, and 3 are the same for all three methods. The only difference is in step 2, where you determine the gammas. Okay, so for MPE, what you're doing is you're solving the system of equations. It's a very small triangular system, which you can write yourself, program yourself. Okay, you solve for the C prime, set Ck equals 1, and then compute this, and then set gamma is equal to that. Okay, this is it. And then you conform your size, as I said before, and then compute SKMP to the x0 plus U sub k minus 1 times psi. U sub k minus 1 is this combination, is this product here. So you perform this operation first, you know the size, you know the RK minus 1, and then you know the QK minus 1, you've saved this vector. So you can compute this thing in a very efficient manner. So for RRE, as I said, 0, 1, and 3 are the same, okay? 2 is different. So here you solve for D, for the vector D. These are two small upper and lower triangular linear systems. Okay, you compute your vector D, and then you compute this thing here called this lambda. You can prove that lambda is real and positive. And once you have lambda, you have D, you can compute your gammas. Okay, and for MPRRE, so SVD RRE, sorry, you compute the SVD singular value decomposition of R sub k. This is enough. This actually will give you the singular values of R sub k are the same as the singular values of U sub k. That's amazing. Okay, and right singular vectors of R sub k are the singular vectors of U sub k. So this is very convenient. Have a very small problem to which we apply SVD singular value decomposition. You get your 8 sub k, okay, and C is equal to 8 sub k, as I said before, and then you form your gammas as follows. Okay, So let me see. I'll talk just a little bit about the convergence property, just one result about the convergence properties. Suppose you have a linear system. So f of x is a linear system, linear function rather. Okay, if you do the iterations, then you end up with vectors whose structures are this. Okay, so vi are actually linearly independent vectors. Lambda I are distinct numbers, different from 0, different from 1. Okay, and then you order them this way, and then you assume that at some point you have lambda k is greater than lambda k plus 1 in modulus. Okay, now, and then what you can show is this. So the approximate, so what is, okay, what are we doing now? What we're doing is, instead of applying these methods to the vectors x0, x1 up to xk plus 1, we now start with x sub n. That is, we're iterating up to x sub n, and then from then on keeping the vectors x sub n plus 1, x sub n plus k plus 1 in the core memory. We discard the rest, okay? And then we call this, the approximation we call snk instead of sk. Okay, so we're asking the question, what happens as n goes to infinity? I have an infinite sequence. I have the extrapolation methods that are operating as a window. You start with n, pick n plus, up to the n plus k plus 1, and then you move this n plus 1 up to n plus k plus 2, n plus 2, etc. Okay, so we ask the question, what happens to the approximations? Okay, under these conditions here, especially the condition that lambda k is greater than lambda k plus 1, then you can show that this error here is of the order of lambda k plus 1 to the power of n. Okay, and here you see in the bottom, lambda k plus 1 is strictly less than lambda k, which is less than or equal to lambda 1. So that means that s sub n plus k and k, sorry, is converging to s faster than the original sequence itself on which it is based. Okay, so this is a convergence acceleration result. Okay, and and then the gammas contain a lot of information. Okay, the information contained is like this. If you form this polynomial here, the limit of the polynomial as n goes to infinity is this polynomial here, whose roots are lambda 1 up to lambda k. That means the zeros of the polynomial, of this polynomial here, are actually approximations to lambda 1, lambda 2 up to lambda sub k. Okay, so let's go on. I think I will skip all this, and I want to show you okay, how do I use this in connection with systems of equations? So you see, you cannot increase n up to infinity so well. You cannot increase k, because if you increase k, then your storage requirements are becoming tremendous. Okay, you don't want to do that. You want to fix your k to fit your computer memory. Okay, so once you figure your k, you can now choose your n, okay, and choose the initial vector x0. And then what you do is you perform these iterations here. Suppose that r is equal to 1 for simplicity, okay? So you form this thing. So you take all these vectors, x sub n, x sub n plus 1, etc., and apply NP or RRE to these vectors to obtain SNK. If your SNK is good enough, you stop. If not, you set x0 is equal to SNK and go to C1. Okay, so this means you're repeating the same procedure over and over again until you get a satisfactory approximation. So this is called cycling in the nomenclature of vector extrapolation methods. The nomenclature of Krylov subspace method is called restarting. Okay, so this is the way we're going to apply it now. And let me show you a few examples. So this is an example of a linear partial differential equation, a Dirichlet problem. Okay, this is the delta is the Laplacian. Okay, and this is a convection diffusion equation. So here we take f equals 0, g equals 0, so that the solution is equal to 0 everywhere. Okay, and we're using central differences to approximate the derivatives here, the first and second order derivatives. And we're using Jacobi iterations on this linear system. So we take here in this example, m equals 30. Therefore, the number of unknowns is 900 now. We take as initial vector this vector here. Now, so let me show you what happens. So let me just one more comment here. So we've applied this thing to this problem. This is the reduced rank extrapolation results, actually, what you see here. So with n equals 0, so you're doing just S0K. You're cycling with that, okay? You see that it's not converging so fast. See, it's converging, but you have to see 100 iterations already, 1200, etc. So it has come down only 2 significant figures. Okay, so this is because of n equals 0. This is a known phenomenon in Krylov subspace methods also, that you have, for example, GMRES, for example, may stall, may stagnate. Okay, you don't see any convergence acceleration. But we have discovered that if we take n sufficiently large, okay, so even a moderate value would do, and you apply S and K instead of SK, then things become dramatically, they improve dramatically. You can see here, we took n equals 50 and k equals 20. So each time 70 vectors, 70, 71 vectors, okay? You can see how this is working so nicely. This is a very nice example, actually, also about how to treat stagnation when you apply extrapolation methods. So this is with beta equals 0 and gamma equals 100. So this was a convergent Jacobi iterations. Okay, now here we are with beta equals minus 100. Now we're close to being close to the regime that the system will, the equations, sorry, the iterations will diverge. Okay, meanwhile they're converging. So n equals 0 and k equals 20, you see, it stalls completely. Okay, when you pick n equals 50 and k equals 20, things come down dramatically fast. Okay, here we have another one. So this one is gamma is 125 and beta is minus 100. This is divergent. You can see divergences here. So these are the iterations that are diverging. And then we apply the reduced rank extrapolation. They come down very quickly. Okay, then they go up again because we're, we're picking the we're picking n vectors before we start the extrapolation procedure. And then they come down again like this. You can see that in about 600 iterations, it's come down 15 orders of magnitude. Okay, here we have another one. Okay, this is a double Jacobi iterations. This has the advantage that when you take double iterations, okay, you may also decrease k by 2, by a factor of 2. See here we had, sorry?
You have 5 more minutes.
Okay.
25, so.
Okay, so here, see the previous slide I had k equals 20 and k equals 20. Now I have here k equals 10 and k equals 10. So, but this is with double Jacobi iterations, that means I have to save about 10 or 11 vectors in the core memory. With 20, I'm saving 21 vectors in core memory, which may be crucial in some cases if your capital N is very large. Okay, so this, you see that, with double Jacobi iterations, you can divide your previous k by 2, and then you obtain such a nice convergence pattern here. Okay, so this is again convergence double Jacobi iterations like this. You can see they're stalling here with n equals 0 and n equals 25. This gives you this one here. So this is okay. So here, just a minute. So this one again with double Jacobi iterations. Okay, this is divergent. Okay, you can see how things are working with n equals 0 like this. You don't see almost anything. With n equals 25 and k equals 10, things behave very nicely. Okay, this was a linear problem. Okay, now we'll go to a nonlinear problem. Okay, this is an application that I did with a fellow at NASA, Lewis Research Center. Okay, and this is a ramjet accelerator. Okay, with 7 species and chemical reactions. Okay, the solution has 2 shock waves, and the computer program, the iterations are very complicated. Okay, now the number of mesh points is 4,000. The number of unknown functions is 10. So you have actually 40,000 unknowns in this problem. This is not such a big problem, but it's for 40,000 is already another small number. Okay, So cost per iteration is very high because the problem is complex. Okay, everything that you do actually is a big program and many computations. Therefore, the cost per iteration is very high, and the overhead of extrapolation is really tiny compared to the cost of one iteration. So here what we did was the following. This one, okay, the first graph that you see here is actually with no chemical reactions. We just shut the chemical reactions. You're just solving the Navier-Stokes equations. That's all you're doing actually.
May I urge you to go to the conclusion? Your time is running out, please.
Okay, so let me show you this. Okay, here no extrapolation. Sorry, the upper curve is no extrapolation. This is with extrapolation. This is with RRE. Okay, the same thing over here. The interesting here, this is the interesting stuff. This is with the chemical reactions. You can see here no extrapolation. This one like this, and with Kmax, okay, you end up with this. So you can see that there's dramatic convergence acceleration in this case. So let me see. So you want me to conclude? I don't have any concluding remarks actually, except for saying that just use them. Or if you have any really complicated nonlinear problems or linear problems that you have to solve, okay, you can probably use these methods also. There are many applications, as I said, in different areas of science and engineering today. Okay, and thank you for your attention.
So we have time for a few questions. So I would like to start off. I mean, you've developed this. I know there are quite a number of quantum chemists in Israel that do things. Why don't you team up with those and have this tested out for the typical problems we have in our community?
Who are the people that you're talking about?
For instance, Igor Shapiro in Jerusalem. He's a program developer. Contact him and proceed with his recommendations who to contact in Israel.
Okay.
Okay, and I see there's a question from Philip, please.
Avram, in the Jacobi example, the passage from the single to double Jacobi, you said that the double allowed you to divide k by 2, and I noticed that n was also divided by 2. Is this fortuitous or systematic? And
No,
how do you find n?
No. So if your original n was 50 and now it's 25, okay, because you're making double iterations, so that's basically you're performing 50 single Jacobi iterations. I just wanted to preserve that. See what I'm saying?
Yes, so you get a factor of 2 on both indices.
Yeah, yes, exactly. Now, the idea there is that if you have an eigenvalue that is close to 1, and 1 is the limit of convergence, basically, if 1, you diverge, okay? So if like 0.9, if you take its square, okay, you get 0.81. It's much farther than 1 than 0.9.
Oh, yes, quite.
You know what I'm saying? That stabilizes things.
And how do you choose n in the first place? How do you find n?
You just try.
Okay.
You try. Okay, but you know, I'm aware of this thing that's called stagnation or stalling. Okay, they talk about this in the application of Krylov subspace methods to linear systems like GMRes and full orthogonalization method. Okay, and one way of getting around this is basically performing some Richardson iterations with the matrix of the system.
All right.
We've done this. We have a paper on this also.
This contribution right now. Once again, thank you, Avram.